Hello and welcome to the Geostatistics course for beginners with QGIS and R. This is the fourth lesson of the course and the topic for today is going to be univariate analysis. But first, let me announce that I created the Facebook page for the Geo RGB community. You are welcome to visit us, like and follow us in this page because I'm going to be posting some things here that you are not going to see on the YouTube channel. For example, yesterday I posted a quiz test related to the construction of a groundwater monitoring well where you can leave your opinion. I'm going to put the link of this Facebook page at the video description. Now let's go to start with the lesson for today. I'm going to do the same as I did at the previous lesson. I'm going to start with some definitions related to the geostatistics. Then at the end of the lesson, I'm going to provide and I'm going to show you how to create the scripts that you can use with QGIS. In geostatistics, we are going to work with random variables. The way we can analyze our data is considering that our variables are random. But what does it mean exactly? Well, let's go to see a couple of definitions. The first one, a random variable is a set of possible values from a random experiment. And the second one, a random variable in statistics is a function that can take on either a finite number of values, each with an associated probability, or an infinite number of values, whose probabilities are summarized by a density function. From these two definitions, I'm going to extract a few sentences. Then I'm going to mark, for example, an important one is a set of possible values from a random experiment. Random experiment is an important one. Also, is a function that can take a finite number of values an associated probability with that values, and also infinite number of values with an associated probability, but in this case it's going to be a density function. All these things are really important. Now I'm going to make my own definition. A random variable that used to be designated with the letter X with a capital letter, take values. These values are x with lowercase in all the range y, and for each value x, that is lowercase, there is an associated probability known as a p in all the range y. And two are the conditions that have to be covered by the probability. The first one is that the probability has to be equal or bigger than 0 in all the range y. And also, the summation of all the probabilities has to be equal to 1. I know all these definitions and all these things look pretty abstract, but now you are going to understand everything well. Let me show you. We have two types of random variables: discrete random variables and continuous random variables. And the difference between these two is that discrete random variables, the outcomes can be counted. But for a continuous random variable, you cannot count the possible values. Is what we saw here at the definitions. We can have a finite number of values or we can have an infinite number of values. For the finite number of values is a discrete random variable, and for infinite number of values it's a continuous random variable. Now let's go to put an example for a discrete random variable. A really good example could be rolling a dice. That is going to be a random experiment, and we are going to have a variable, and that variable that is x capital letter is going to have 6 possible different values. Is all these values. We can have number 1, 2, 3, 4, 5, or 6. That's the set of values for this variable. As we said previously, we have a set of values from a random experiment. Then let's go to calculate what is the probability of getting the number 1. The probability of getting the x, this one is a lowercase, equal to 1, is going to be 1 divided by 6. We are going to have just one case divided by the total possible cases. That is going to be 6 cases. Okay, that's the probability of getting the number 1. And now what is the probability of getting the number 2? Then it's going to be the same. The probability of getting the x equal to number 2 is going to be 1 divided by 6, because we are taking just the number 2 divided by the total possible cases, that is 6, is going to be the same, 1 divided by 6. Then for 3, 4, 5, and 6 is going to be the same probability. Then what is the total probability of all the possible cases? Then in this case is going to be the probability of getting the number 1, or getting the number 2, or getting the number 3, or 4, or 5, or 6. Then that probability is going to be 6 possible cases divided in the total cases, that is 6. Then 6 divided by 6 is going to be equal 1, and that is going to be the total probability. And then with this definition we are covering all the things that we was saying over here, right? The probability is equal or bigger than 0, and the summation of all the probabilities is going to be equal to 1. And also we have a function. Now I'm going to show you the function, and we was doing all these things, right? We have a variable that is designated with the capital letter X, and also we have values associated with that variable, and each of these values has a probability associated. The function in this case is this one. This is the function for this discrete random variable. In this case, it's pretty evident that we can count the possible cases, right? Another example of a discrete random variable could be flipping a coin, where we are going to have the variable x as a capital letter, and we are going to have 2 possible outcomes. That could be to have face or to have tail. Another example could be the people who has a red car. We can count all the people that can have a red car, right? Then that is a discrete random variable. In this course, we are not going to work with this kind of variable. We are going to work exclusively with continuous random variable. And now I am going to define this one. Let's go to suppose that we are doing a study of arsenic concentration in soils, and we know that the concentration in that soil for arsenic goes from 0 ppm to 10 ppm, and we have a sample that the value is 1.3 ppm. And the question is, do you think that this value is 1.3? It means that the value is 1.300000 until the infinite, and the last number is going to be 1, because we have infinite number of decimals. We are 100% sure that this value is this value, or maybe this value could be this one, 1.332, or maybe 1.333, or maybe it could be 1.321, right? The values that we can have in this point, it's infinite, because the number of decimals are going to be infinite. Then in this case, when we are talking about continuous random variables, the possible values that we can get, it's infinite. From this range, from 0 to 10 ppm, we can have an infinite number of samples, an infinite number of values. Then the question is, can we calculate the probability in this exactly point? The answer is it doesn't worth it, because let's go to imagine that the x lowercase is the value that we want to calculate the probability. Then we have one possible case, is this one, but how many potential cases we can get in this range is going to be infinite. Then 1 divided by infinite is going to be 0. Then the probability of getting this sample in this range is going to be 0. For the continuous random variables, what we are going to do is calculate the probability in a range. For example, in this case, we are going to say that we want to calculate the probability of getting a value, for example, from here to here. And that range could be, for example, from A to B. That's what we are going to do when we are working with continuous random variables. Let me put here 20. And the function associated with this variable is going to be this one. The variable is the capital letter and is the concentration of arsenic in soil. And we have a set of values, and this set of values are in a specific range. And about the continuous random variable in geoscience could be a lot of different things, right? Could be, for example, the temperature of the soil, could be the concentration of a contaminant in groundwater, could be the precipitation in a specific area, and so on. It's the kind of variables that we cannot count the possible values we can get if we make the difference with discrete random variables. And again, in this case, in continuous random variables, we are covering all these assumptions. We have a set of values, it is a function, it has an infinite number of values, and we have the variable, it's a X capital letter, where we have some values that is lowercase, and all these values has a probability associated, and the probability has to be bigger or equal than 1, and also the summation of all the probabilities is going to be equal to 1. But for a continuous random variables, we are going to use a cumulative distribution function or the probability density function to calculate the probability. One thing that I don't like for geoscience when we are talking about continuous random variables is about the random experiment. And that's the reason because I write this sentence here. Let me show you. Are the set of data distributed randomly? And the answer is not. But there is uncertainty, and that's the important thing, right? However, if we treat the data as a random variable with an associated cumulative distribution function or with a probability density function, we can model the data. And I believe that's the point. If we are considering that our variables in geoscience are continuous random variables, we can use all the sources, all the tools from the theory of the probability to model our data and make an interpretation and understand how our data, the behavior of our data, right? For me, it is very hard to think that the phenomena that happen in geoscience in most of the cases are random experiments. For example, if I have a contaminated soil, it is because there was a spill over there and the spill was not random. Or maybe if I have a highest concentration in one specific point, is because maybe the groundwater moved the contaminant from one point to a different point. Or maybe I have the highest concentration in a specific contaminant over there because there is the focus of the contamination. It's not something randomly, but it is something that has uncertainty. And because of that, we can use the theory of the probability. Let's go to put an example, just to try to clarify this situation better. Let's go to imagine that we are saying that our distribution of our data is following a sinus distribution, okay? Then we are going to have something like that. That's the function for the sinus of the x. And this one is a deterministic model, okay? Then we have three samples here, one here, one here, and one here. And with these three samples, we have already our model. And we know everything about this model. We know that we are not going to have a sample over here, and we know that we are not going to have a sample over here, because all the samples are going to be on the line. And now we have already the model. We don't have to do anything more, right? But in geoscience, what happened is that we have one sample here, for example, one sample here and one sample here. And then we are going to say that our model is doing something like that. But that's not the reality, because that's just a probability. Maybe the model is doing something like that. And we don't know that one, right? And even one very good example is when in geoscience we add more data to the model is going to change. Let's go to imagine that now we add a couple of more samples. This one and this one, for example. Then the model before was something like that. But now, as we added extra samples, now the model is doing something like that. However, when we are having a deterministic model, the model never changes, it's the same. But for a probabilistic model, it can change every time we add different values on the experiment, right? Well, hopefully you understand my point of view. Now let's go to move on to the cumulative distribution function, where with this kind of function, a lot of things that we explain related with the continuous and random variables are going to be understood. I'm not going to extend too much with this slide because to explain the cumulative distribution function is better with a real example. I'm going to read the definition. The cumulative distribution function, known as a CDF of a random variable, x as a capital letter, is the probability that that variable, x as a capital letter, will take a value less than or equal to x lowercase. Then this one is the function, and the probability associated with this function is this one, and this function is defined in a specific range that goes from 0 to 1. As you can see here, from 0 to 1. And the y-axis is the probability, and the probability, the maximum can be 1 or 100% if we are talking in percent, right? And for the x-axis, what we are going to have is the different values for our variable. That could be temperature, pH, electroconductivity, concentration of something. And what we are going to do is establish the probability of having a sample in a specific range. For example, from here to here, the probability of having a sample in this range is going to be the intersection of this line, the vertical line, with the horizontal line in this curve. Then this probability is going to be this point over here. It is important to say that the cumulative distribution function is designated with the letter F as a capital letter, because in the probability density function, the letter is going to be F as a lowercase. Now let's go to see a real example. Let's go to create the script on using R in QGIS. At the previous lesson, we was working with the data set related with groundwater, with the groundwater elevation. Today we are going to work with the Meuse River dataset, and the variable is going to be the concentration of zinc in soil in parts per million. Then let's go to load. That dataset is this one. Open, and we was talking at the previous lesson about all these things. As you can see, the attribute table here, we have the UTM coordinates, and we have several parameters related with heavy metals concentration in parts per million, and we are going to work with the zinc. There are also different parameters that we are not going to use, like elevation, distance, type of soil, land use, and etc. Then I'm going to add this one. Okay, and I'm going to close, and I'm going to add a satellite imagery to give the points some geographical context. And today I'm going to use Esri, and I'm going to add the satellite imagery. I'm going to change the color for the dots. It's going to be an orange color. That one is okay. And let's go. First, before to create the new script, I would like to see the histogram related with the zinc concentration. Then to do that one, we are going to use the last script that we created the other day. Is this one here is going to be the number 4, and the layer is loaded automatically because we have just one. The parameter is going to be the zinc. The number of bins, in this case, let me check one thing. In this case, we can see how many samples we have. And if you check this column, the field, We have from 1 to 164, but that is wrong. It's better if you see here from 1, that one doesn't move, then we can go like this, and the total is 155. There are some missing values over here, okay? The total is 155. Then in order to do a good number of bins, what we can do is use the calculator, and then what I'm going to do is the root square of 155. 155, the root square is 12.4, and I'm going to use then 12 bins. The number of bins is extremely important and has to be representative of your data. Maybe we are going to talk about these things in a different lesson, but it is really important. And you can use, if you have more than 100 samples, you can use the root square, but you have to see if the graph represents the data well. If not, you can change the number. And if you have less than 100 samples, you can use 9, 8, depending how many samples you have, okay? Then for X is going to be the concentration of zinc in ppm. For Y is going to be the frequency, and the title is going to be histogram, and the subtitle is going to be raw data, because we are not going to make any modification in the data, and I want to specify that the data is raw. Then I'm not going to save, and I'm going to run right away. And here we have the result. What we can see on the distribution of our data in the histogram is that most of our data is located in this concentration. From here, that it's not 0, it's going to be, the minimum value is 113, I believe. From 113 to 500, we have the most of the samples. Then here in this area of the graph, we have just a very few samples. You can see the frequency here, maybe this value is 1 or 2, and here 3 or 4, but here we have almost 60 samples, and here we have almost 25, and so on. Also, the distribution in this case is not normally distributed. The skewness in this case is really important, and if we are thinking to do a Kriging interpolation or cokriging interpolation, we have to think in this case to make a transformation of our data, because here these values here are making a modification, a big modification of the mean of our data. Then we have to do a logarithmic transformation in this case. But we are going to talk about the transformations in a different lesson. Now let's go to create the cumulative distribution function. Go here, I'm going to close this one. Then go here, create new R script, and I'm going to paste over here. Going to make this one bigger. We was talking about all these things at the previous video. That's the group for the script we are going to create. That's to show the plots. That's the kind of layer we are going to extract information. That's the parameter we want to analyze. That is for the labels for X and Y. That's for the title, and this one is for the subtitle. And the package we are going to use is ggplot2. That is one of the best to create graphs, and that's the script. The first part is for the parameter that we are going to analyze. The second part, I'm going to move this one here, is going to create the cumulative distribution function. And the line is going to be blue color, and the size of the line is going to be equal to 1. Then this one is for the labels, for the X and Y, and also to add the title and subtitle. And these three are specific themes that we are going to use to edit the title, subtitle, and also the number at the axis. And let's go to save this one as a cumulative distribution function, as a number 5. Save, and we can close, and we can run the script now. Then here is going to be the number 5, double click, and the layer, as it is the only layer that we have as a vectorial one. It loads automatically. Then the parameter is going to be zinc. For X is going to be the concentration of zinc in ppm. For Y is going to be the probability. The title is going to be Cumulative Distribution Function, and the subtitle is going to be raw data, for example. I'm not going to save the file, then I'm going to run. And let's go to open. And this is the graph. Now I'm going to copy this one and I'm going to open with this software, and we are going to make some things. First, we are going to see how we can calculate to have a probability of having a sample that the concentration is equal to 700 ppm or less. Then what we are going to do is recognize what is the 700 over here. Then we are going to make a vertical line until we get the curve. Then when we get the curve, we are going to make a horizontal line, and we are going to see what is the probability in the y-axis. I make all the lines for 700 ppm over here, and then I calculated the probability is that one over here, and the probability of having a sample in this range from here to here is going to be 0.76. Now what I'm going to do is calculate what is the probability of having a value that is equal to 150 ppm or less. Then as you can see over here, we have 250. Then I calculated approximately the 150 ppm is over here. Then I make the vertical line. Then when the vertical line touches the curve, I make the horizontal line, and I get this value. And this probability is going to be 0.125. Now, as we have these two probabilities, we can calculate, for example, what is going to be the probability of having a sample that is bigger than 700. And that one is going to be pretty easy. What I am doing in this case is the inverse. I want to calculate this probability, and I know how much it represents 700 ppm. Now I want to know what it represents all this range until here, right? Until the highest value. Then what I'm going to do is make one less this probability. Then I'm going to get the rest, is all these samples over here. And the probability of having a sample that is higher than 700 is going to be 0.24. Now what we can calculate, what is the probability of having a sample that is between 150 ppm and 700 ppm. What I'm going to calculate is all these samples here. What is the probability of getting any of these samples over here? Then in that case, what we are going to do is take the probability of having this sample from 0 to 700 ppm. I mean from here to 700 ppm, and then I'm going to take the 150 from here to here, and that's what I'm doing here, right? What is the probability of having a sample between 150 ppm and 700 ppm? Then I'm taking this one, is this probability less this probability. Then what I'm going to get is all these samples over here. That is the probability, and it's 0.635. In 10% is going to be 63.5%. Now we are going to see how we can extract from this graph the most common quantiles and also the median. Then what we have for the first quantile, that is the probability of 25%, is going to be this one. Then what we have to do is make a horizontal line, and then when this horizontal line touches the curve, we are going to make the vertical line, and then we are going to get the value related with the zinc concentration. In this case, for the first quantile, is going to be 200 ppm approximately, okay, because that one over here is 250. Then for the second quantile, that is the median, the probability is 50%. Then it's going to be this one. I'm going to do the same, make the horizontal line, and then make the vertical line, and the value for the median for this data set is going to be 320 ppm. Then the third quantile is for the probability associated with a 75% is over here. Then I'm going to do the same horizontal line, then the vertical line, and the concentration I'm going to get is a little bit less than 700. It's going to be 698 ppm. Then as you can see, we can calculate the probability just making vertical lines and then horizontal lines, or we can calculate the concentrations from the probability just making the horizontal line and then the vertical line. Now let's go to see some information that we can get from this graph related with the distribution of our data. If we make a line that is going to be a quite vertical line from here to here, just covering all this area of the curve, what we are going to see that when we have a vertical line, it means that we have a very small range of values that represent a lot of the samples that we have. As you can see in this case, from the lowest value is 113, as you can see here, the lowest is 113 and the highest is 1839. Then we have almost 50% of our samples that goes from 113 to maybe 260 or 70 over here. And that's what this vertical line represents over here, that we have a lot of samples that are accumulated at the beginning of the range. And that's what we are and that's what we can see on the histogram, right? It's the same information, right? We are seeing here that most of the samples are located in this range, as you can see the bins and the frequency. Also, other information, sorry, let me move over here. Other information is when we have a horizontal line, right? Over here we have some horizontal lines, and how we can make the interpretation of that horizontal lines. Let me put this one here. When we have something like that, could be two different options. Could be that we have a very few values, or maybe we don't have any value, and then we are going to have a horizontal line. And that's what we can see also at the histogram, that we have just a very few values in this range, and that's the representation over here. Then the X scenarios that we can have, it's a lot of different X scenarios, right? Maybe we have something that at the beginning maybe it's very flat, then goes up a little bit, then maybe goes flat again. That could be something that it's pretty normal distributed, right? Then maybe we can have something that it's very flat at the beginning, then goes up very fast, and then goes flat again, something like that, right? Indicating that most of the samples are located at the middle, right? With having a normal distributed with a very low standard deviation. We are going to talk about this parameter in a different lesson. Also could be something, I don't know, could be a lot of different things, right? Something like that, flat, then goes up, flat. But one thing that is very important is this line always has to go up, okay? You are not going to see something like that. For example, goes up at the beginning, then goes flat, and then go down. Something like that. If we have something like that, it's not good, because what we are going to see that all these values are negative probability, and that it's not correct, right? Because we have to cover this assumption related with the probability, where the probability has to be equal or bigger than 0 in all the range y, and also the summation of all the probabilities in this range has to be equal to 1. And that's what we are seeing over here, right? That always this one is positive, even sometimes it gets flat, but it's always positive. And the total summation of all the concentration is going to be equal to 1 or 100%. Now I'm going to explain how you can make the construction of this graph. First, what you need to know is that this curve has been created with the bins. Each of these steps is one bin. In total, we can have as a maximum of 155 because that's the number of samples we have. But even that one is going to be less because sometimes the concentration is the same and then we are not going to have any bin. Then what I did is make the summation of all concentrations, and that's the result. Okay, that's the total. That represents the 100% or one value for the probability. Okay, and I make this relation here. For this concentration, that is the total summation of all concentrations, is 100%. And what is going to be the high, this high over here, for the concentration of 113? That is the first concentration that I have, the minimum value. We go to the table, the minimum value, as you can see, is 113. The second one is 117, the third one is 119, and the fourth one is 119, okay? Then for the high, I'm going to make this equation. Then I'm going to multiply 113, that is the first concentration, per 100. Then I'm going to divide by the total summation of the concentration. Then I'm going to have the 10%. Then I'm going to divide this number by 100 and I'm going to get the probability. Then now I have the high over here for the first value, for the first bin. And what is going to be the weight of that bin? Then it's going to be the concentration of the second concentration less the first concentration. As we saw here at the attribute table, the second concentration is 117 and the first one is 113. I make the difference and I get the weight for the first bin. And that's what I did here. The first bin is the first step. What is the weight? It's going to be 4 units. What is the high? Is 0.00155. Then what happened for the second bin? Then the second bin, we have to add the concentration of the first bin because this one is a summation. We are making a summation, okay? Then let's go to see. What is going to be the high? Well, the high for the second bin, we are going to make the summation of the first bin plus the concentration of the second sample. The second value, I mean, because you know that one is in order, okay? Then I made the summation of these two for the second bin. Then I multiply by 100 and divide it by the total summation of the concentration. Then I'm going to have this value in 10%. Then I'm going to divide it by 100 and I'm going to have the high, that is the probability, the high for the second bin, okay? And how wide is that bin? It's going to be the third concentration less the second one. Then it's going to be 2 units. Then I'm going to go to the graph. For the second step, it's going to be 2 units. Even here is the same way. I cannot make this one the half, okay? Just to have an idea. Then I have the high and also I have the y. Then I can make these 2 bins, okay? To make the curve. For the third bin, it's going to be the same. But now I have to plus the third concentration. Is the first concentration, the second concentration, and the third concentration, okay? Everything is plus because it's cumulative. Then multiply by 100 and divide it by the total concentration. I get this 10%. Then I divide it by 100 and I get the probability. That's the high. Then what is the y? In this case, as the third concentration and the fourth concentration is 0, I don't have any y here. Then my line at this curve is going to be totally vertical because I don't have any y in that position. And that's the way how we can make the construction of this curve. Well, that's the end for this lesson. Thank you very much for watching and see you on the next one.